Welcome to the fifth lecture of our Introduction to Modular Forms. So, a quick recap of what we did last time. So, last time we defined what a modular form is. So, basically, a modular form is a complex holomorphic function that is one periodic, that is f of z plus 1 is f of z. And we have another condition that f of negative 1 over z is equal to z to the k f of z. So if this happens, we call the function f a modular form of weight k. And then we've seen an example of a modular form that we called the Eisenstein series. So the Eisenstein series was defined like this, is equal to a sum of 1 over mz plus n to the power k. And this sum is over all the integers m and n such that not both of them are 0. So not both of them are 0 and m and n are integers. So, and we have seen that this sum converges for even k greater than or equal to 4. Yeah. And also, I think I've given an exercise to prove that E sub k z is equal to 1 over 2 zeta of k g k of z, right? Where E sub k is defined as sum over 1 over mz plus n to the k, where m and n are co-prime. Right? So E sub k is called the normalized Eisenstein series, and today we'll see what this term normalized means. Okay, and G sub k is the sort of the unnormalized Eisenstein series. So today, the key topic for us today is the Q expansion. So let us start with a theorem. So that theorem actually works for any complex holomorphic function with some extra condition. That complex holomorphic function need not be a modular form. So let us state the theorem. Suppose f is a holomorphic function from the upper half plane, and f is bounded, sorry, not bounded, like f is periodic with period 1. That is, f of z plus 1 is equal to f of z for every z in the upper half plane. And we have another condition, that is, f is bounded as image of z goes to infinity. Okay, so this was our third condition for modular forms. And I think I didn't mention this, that if f is not bounded as image of z goes to infinity, then we call it a meromorphic function. Sorry, a meromorphic modular form. Sorry. And sometimes they call it weak modular form. Yeah. Okay, but yeah, we'll be.
Why do you call it image of z instead of imaginary part?
Yeah, imaginary part of z. Sorry. Yeah. So if f is the holomorphic function on the upper half plane, and f is periodic with period 1, and also f is bounded as the imaginary part of z goes to infinity, then there exists a sequence of complex numbers, such that f of z is equal to a sum of an e to the power 2 pi I n z, where n runs from 0 to infinity. Yeah.
Does it have to be like one periodic or work with any period?
I believe it works for any period, because then you just need to like modify this part. So already you can see a lot of similarities with Fourier series. And yeah, so we'll need what a Fourier series is. Okay, but yeah, let's try to prove this theorem. Okay. First of all, we define a function q from the upper half plane to the punctured disk. So this is the punctured disk, that is all the complex numbers with their modulus being smaller, strictly smaller than 1 and strictly positive. So this is the punctured disk. So this is basically the open ball except the center.
Indeed.
Yeah. And this function will define as q of z is e to the power 2 pi I z. Okay. And if we take the absolute value of this thing, so the absolute value of e to the power 2 pi I, let's write z as x plus iy. So this is equal to e to the power minus 2 pi y, right? And since z is in the upper half plane, y is positive. So, and since y is positive, this thing is in 0, this interval, right? So indeed, this is the function from the upper half plane to the punctured disk. All right. And another thing that is, this function is surjective. So why is it surjective? Like given any point in the punctured disk, we can write that point as r times e to the I theta, like this, right? Well, we can even write it like e to the 2 pi I theta, right? And yeah, and since r is a number from 0 to 1, so we can write r as e to the negative 2 pi y. And yeah, and the choice for y is unique in this case, right? So yeah, and yeah, and but the thing is, the choice for theta is not unique. Okay, so here, like the value of theta, theta plus 1, theta plus 2 all give the same point, right? So this is a surjective map but not injective. Okay. Let me write it again. So this is equal to like q of theta plus, let's see, this is, so negative 2 pi y is log r, so y is log r divided by negative 2 pi, right? So theta plus I log r divided by negative 2 pi. Okay. And also like theta and theta plus n, for n being any integer, gives same output. Okay. So yeah, so we've seen that Q is a surjective map. All right. Now we are going to define a function f tilde from the punctured disk to a set of complex numbers, and we'll define this as follows. So, okay. So given some, so let's take a value like z from the punctured disk. Then we know that like z is equal to like q of like tau for some tau in the upper half plane, right? Since q is a surjective map. Then we define f tilde of z to be f of f of tau. All right. So we need to actually check the well-definedness of this definition, because we have multiple choices for tau, right? So and you can see that all the multiple choices of tau are basically like tau plus n, where n is a integer. And we already know that f of tau is exactly the same as f of tau plus 1. So by induction, it's the same as f of tau plus n for any integer n. All right. So this is indeed a well-defined definition. Okay. Now we need to check whether this is holomorphic or not. And in order to check that this is holomorphic, we'll take a different path than we've taken before. So we are going to compute the derivative explicitly. So if we can show that the derivative exists, then we're basically done, because complex holomorphic functions are basically extensions of differentiable functions, right? So yeah, so we need to compute f tilde of z minus f tilde of z naught divided by z minus z naught, and we need to compute this limit. So we need to compute limit as z goes to z naught, right? So basically we've taken any z naught and z, and we can write it like this. So we can write it like f of tau minus f of tau minus f of tau naught divided by z minus z. And what are tau and tau naught? So z is equal to q of tau, and z naught is equal to q of tau naught. Okay. And another thing that is, since we can take z and z naught to be really close, so for sufficiently close z and z naught, we can choose tau and tau naught to be sufficiently close as well, right? Okay. Then we can rewrite this as so f of tau minus f of tau naught divided by tau minus tau naught divided by z minus z naught. Okay. And yeah, let us write this thing. So how did we define q? Q was e to the 2 pi I tau, right? Then this is f of tau naught, tau minus tau naught, and this is tau minus, sorry, tau minus tau naught, e to the 2 pi I tau minus e to the 2 pi I tau naught. Okay. Then if we take the limit as, so we are taking the limit as z goes to z naught, right? And we have we've said that as z goes to z naught, tau goes to tau naught as well. So if we take the limit z goes to z naught, then we get this is f prime of tau naught, right? And this is 1 over 2 pi I e to the 2 pi I tau naught, right? So this is the the reciprocal of the derivative of e to the 2 pi I tau. All right, so then we see that this is equal to f prime of tau naught divided by 2 pi I q of tau naught, and q of tau naught is z naught, right? Okay. So therefore we have seen that f naught is differentiable because the derivative exists at each point of our domain, right? And it's differentiable, so therefore it's holomorphic. All right. And it's holomorphic in the punctured disk. Okay, so now you can see that this is the origin, this is our punctured disk. So we can consider this origin, sorry, we can consider this punctured disk as an annulus. Okay, an annulus with like inner radius being 0 and outer radius being 1. So, so this is an annulus centered at 0 with inner radius 0 and outer radius 1. And what is this annulus again? This is the set of all the complex numbers such that the absolute value of z is between 0 and 1. And if these inner and outer radiuses are like are with are values with other than 0 and 1, then we basically change these two values. Okay, so that's how annulus is defined. And I think we've seen that if a function is holomorphic in an annulus, then there exists a Laurent series. Right? So therefore, there exists a Laurent series around our center of the annulus 0. So therefore, f tilde z is equal to a n z to the n, where n is integers, right? Okay. Now we are going to pull up the last card. Okay. So the last card is this one. F is bounded as the imaginary part of z goes to infinity. So as the imaginary part of z goes to infinity, I think, yeah. Yeah. So imaginary part of z goes to infinity. So this corresponds to like so my claim is that those points correspond to this origin. Okay, why is that? Because like what was our definition of q? So q of tau was e to the 2 pi I tau, right? And this is, if I write tau as x plus iy, this is e to the 2 pi I x e to the negative 2 pi y, right? So if the imaginary part of tau goes to infinity, that is, if y goes to infinity, this goes to 0. So, so all those points represent like z equals to 0 in here, right? And like as imaginary part of tau goes to infinity, z goes to 0. So where z is basically this. Okay. And yeah, and I think I need to like freshen up the notation a little bit. So let me write this again. So q of tau is z, and f tilde of z is equal to f of tau, right? So yeah, so z goes to infinity, sorry, z goes to 0 is equivalent to imaginary part of tau goes to infinity, right? And as imaginary part of tau goes to infinity, f is bounded. All right. So therefore, the limit z goes to 0, f tilde of z. This is finite. So since this is the finite limit, in the Laurent series, the coefficients with like negative index must be 0, because otherwise this limit diverges. But we've seen that this limit is finite. So therefore, the Laurent series must be equal to a n z to the n, but n is starting from 0. So this is no longer a Laurent series, this is a good old power series. And yeah, so, and also what was z? Z was like q of tau. So we can write that f of tau is equal to sum of a n, z is e to the 2 pi I tau n. N runs from 0 to infinity. which is what we wanted to show. Okay. So it's a common abuse of notation to write like q and q of tau with the same symbol. Okay. So in a lot of the literatures you can see like this abuse of notation. And then like yeah. So then f of tau is like written like sum of a n q to the n. Okay, because what is q? Q is basically q of tau. So they write it with the same symbol. And this expansion is called the q series expansion. Yeah. So this is called the q series expansion, where q is e to the 2 pi I tau. Okay. And the coefficients an, so let me write it. This is q series expansion. Some people say this q expansion. Okay, and the coefficients an are called Fourier coefficients. Okay. Yeah. Yeah. Also, there's another like very common abuse of notation, that is people write f and f tilde with the same symbol. I don't quite like it, but I'll try to be consistent with my notations. But yeah, like you people should be like cautious while reading other literatures, that like people write these two to be the same, but they are actually not. So the f is a modular form, is a function from the upper half plane, but f tilde is a function from the punctured disk. Okay, so these two are not the same. Also, okay. So yeah. So let us write the q series expansion again. F of tau is sum of a n q to the n, and like we had like two functional equations for modular form, right? One is that f is one periodic, and f of negative 1 over tau is tau to the k f of tau, right? The first condition is easily encoded in this equation, right? Because q is nothing but e to the 2 pi I tau. Okay, so the well-definedness of this sum right here is basically tells us that f is one period, right? So if we just like replace tau by tau plus 1, then we just get e to the 2 pi I tau plus 1, and that is nothing but wait, yeah. So that's just e to the 2 pi I tau and e to the 2 pi I. And e to the 2 pi I is 1. So this property right here is easily verified. I should rather say this property is easily encoded in this Q series expansion. But the second condition is not really manifested in this equation. And it's actually quite difficult to like formulate modular forms using Q series expansion. So first we define modular forms using our like usual definition, then we give the Q series expansion. So the other way around is not really very easy. And also, if we are given a power series, let's say sum over Cn q to the n, like power series in D. D is the unit disk. Okay, we are no longer in the punctured disk because this power series is here n starts from 0. Okay, so since n starts from 0, then this is like holomorphic on the origin as well. Okay, so yeah, if you are given a power series in the unit disk, then usually there is no simple way to check that whether this is a modular form. Like sorry, this is the Q series expansion of a modular form. So usually there's no simple way. So you need to like get back to the original f from this is f tilde, right? So from this f tilde, you need to get back to the original f to check that whether that is a modular form or not. So from this Q series expansion, there's no simple way to like show whether it's a modular form or not. So if you can find a simple way to show that show from the Q series expansion that this is a modular form, then well, the mathematical community will like celebrate your excellence. Yeah, very definitely. Yeah. Okay. All right. And like last time we've seen that like well modular forms are not something we made up, they certainly exist. Okay, and the examples we've seen were the Eisenstein series. And now we have seen a like new construction from the modular form. So it's a natural thing to like ask that what are the Q series expansion of the Eisenstein series. So we'll jump into that. But before that, we need some background of Fourier transformation. Okay. And we'll derive the Poisson summation formula. Then we'll get back to the Eisenstein, the Q series expansion of Eisenstein series. Okay. Let's say we have some function, complex valued function that is absolutely integrable. Absolutely integrable. So what do I mean by absolutely integrable? That is the integral of absolute value of x from negative infinity to infinity. This is finite. Okay. So yeah. So suppose f is an absolutely integrable function. Of course, f must be continuous. Then the Fourier transform of f, Fourier transform of f is defined as follows. F hat of y is defined as an integral negative infinity to infinity f of x e to the 2 pi I xy dx. So this is the Fourier transform of f. And yeah, and well, this is an integral from negative infinity to infinity. So we need to verify that this is a finite number. Otherwise, this function is not well defined. So let us now check that. So this is the absolute value of the integral. So I'm not writing this whole thing again. So and this is smaller than or equal to the integral of f of x e to the 2 pi I xy. Right. And the absolute value of 2 pi I xy is 1 because x and y are real numbers. So this is nothing but the integral of f of x dx. So indeed, the Fourier transform is well defined, given that f is absolutely integrable. All right. Okay. And there's also another very interesting result about Fourier transformation. So yeah, that is suppose now we have this function f hat. Okay, so we can compute the Fourier transformation of f hat, right? So what will be the Fourier transformation of f hat? That is f hat y e to the 2 pi I xy dy integration negative infinity to infinity. So this should be the Fourier transform of f hat, right? And this is equal to f of x. Well, not quite. We have a negative sign in front.
So this is reverse.
Yeah, so this is the inverse Fourier transformation. Okay. Yeah. Right. So you can verify this very easily. For that, you need to compute some integrals. And if you are like, familiar with distribution theory, then this is like related to the Dirac delta distribution. Okay, I think I can show that real quick. So yeah, so what is this? This is equal to, let's say, sorry, I think it's better if I write it like this. F of x to e to the power 2 pi I xy, this is the f hat, then I get e to the negative 2 pi I have to write it x prime because x and this x and this x are not the same, dx dy, and both the integrals are from negative infinity to infinity. Okay, so if we first evaluate the y integral, then we get this f of x delta of x minus x prime. And the delta of x minus x prime is defined as the Fourier transform of the not the identity, Fourier transformation of the constant function 1. So this is the constant function 1. Okay, that maps everything to 1. So the Fourier transformation of that constant function is the Dirac delta distribution. And yeah, if you are familiar with this distribution theory, then you can say that, well, this is exactly equal to f of x prime. But yeah, so that's not the main focus of us today. So we're going to assume this is true, like we did in the group theory and complex analysis review parts. Okay. All right. So that was Fourier transform. Now we have like another thing that is Fourier series. Okay. So what is Fourier series? Suppose I have a function f that is periodic. Periodic, let's say with period L. Okay. So then our function f is no longer absolutely integrable because from 0 to L we have a certain value of the integral. From L to 2L we have like the same part repeated again. So if we compute the absolute integral, so that integral is going to diverge. So yeah, so now we have a function that is periodic with period L. Then the Fourier series tells us a way to write the function as a like sum of as a sum of plane waves. So yeah. And yeah, so the Fourier transform of this function f, which is not absolutely integrable. So the Fourier transform of that function is defined like this. F hat of k is defined as an integral, of course, f of x e to the power 2 pi I kx dx, and the integral is now from 0 to L because the function is L periodic. That's all. And yeah, and like last time we have the formula for the inverse Fourier transformation again, but this time we have a summation. K is an integer e to the negative 2 pi I kx. So yeah, so like these are the formulas like we are like assuming to be true for now. Okay, does anyone have any question? All right. Now we're going to derive the Poisson summation formula. So yeah. So suppose f is a let's say complex valued function on the real line, and f is absolutely integrable. All right. Then the Poisson summation formula says that the sum of Fn as n varies over the set of integers is exactly the same as the sum of f hat n as n varies in the set of integers. And f hat is the Fourier transform of f. So let us try to prove this. So for that, we shall define another function, capital F, and that function is defined as sum of f of x plus n as n is integer. Okay. Okay, can someone tell me like why this sum converges absolutely?
If it's periodic,
Which f? Small f or capital F? Small f is not periodic. Small f is just an absolutely integrable function. And yeah, ideally we want to show that capital F is periodic. But in order to show that capital F is periodic, like saying that capital F is periodic with period 1 is the same as saying that we can basically rearrange the terms in this sum.
it's absolutely
Yeah, F is absolutely integrable. Exactly. So what Tanmoy was saying is that F absolutely integrable means that the integral of the absolute value of x, this is bounded, right? And we can approach this integral like this, like let's say 0 and from 0 and 1, like we're going to take the height with f of 0. Okay, so this is the height f of 0. And from 1 to 2 we can take the height f of 1. So yeah, let's say our function is like this. Okay, so this is not a very good picture, I guess. So in the interval 0 to 1, we can take a rectangle with height f of 0. And in the interval 1 to 2, we can take the rectangle with height f of 1. And in the negative direction as well, we can do it similarly. Oh, so, sorry. I've made a small mistake. That is, with height not f of 0, but absolute value of f of 0. Right? And since f is absolutely integrable, so this so the sum of the area of these little boxes, rectangular boxes, they must be finite. Since these boxes are used to like approach the integral of absolute value of f. Okay. So since f is absolutely integrable, this sum converges absolutely. So since it converges absolutely, then we don't have any rearrangement issues. So we can like rearrange the terms and get the same summation. So therefore, f of x is exactly the same as f of x plus 1. Okay. Now that we have that capital F is one periodic, so we can take the Fourier series of capital F, right? So the Fourier series of capital F. So this is the Fourier transform Fk, and that is like the integral from 0 to 1 of capital F x e to the 2 pi I kx dk. Is that right? I think so, yeah. And this is 0, 1 summation of f of x plus n e to the 2 pi I kx dk. And n, as always, is an integer. Okay. Now, yeah. So this sum right here, it converges absolutely, as we have seen earlier, right? So therefore, we can switch the order of summation and integral. So this is f of x plus n e to the 2 pi I kx dk. All right? Okay. And now I'm gonna do a change of variables. That is, yeah. So now I'm gonna do a change of variables and write it like this: n is in z. This integral is from n to n plus 1 f of x e to the 2 pi I kx dk. Okay. So what did we do? We basically like shifted x. So like x was like x started from 0 to 1. So, sorry, not x. We have shifted k. I'm sorry. So k was in the interval like 0 to 1 before, but now k is in the interval like e. Sorry, I think I've made a mistake that this integral is supposed to be over x. Right, right. I'm extremely sorry. Did I make the mistake earlier? No, the earlier versions are fine, I think. Yeah. Yeah, the integrals are over x. I'm sorry. Okay. I need to change the e to the x. Well, that's a very good point, but actually I don't need to change it because n is an integer. So let us write the change of variables more explicitly. That is, from here, I'm writing like x plus n is equal to, let's say, some other variable u. So then the integral becomes integral. So as x is 0, u is n, x is 1, u is n plus 1. This is f of u e to the 2 pi. So dx and du are the same, 2 pi I k. X is u minus n. Right? So this is the integral. And 2 pi I k n. And e to the power 2 pi I k n is 1. Since both k, since n is an integer, sorry. Yeah. So this is the thing. And yeah, of course, now we can write it like this is an integral from like negative infinity to infinity. F of x e to the 2 pi I kx dx. And what is this? This is nothing but the Fourier transform of f at k. So what did we prove? We proved that the Fourier transform of capital F is the same as the Fourier transform of small f. So yeah, and since f is like one periodic, right? F was one periodic, so the Fourier series of f is f of x is equal to sum of f hat of k capital F hat of k e to the negative 2 pi I kx as k runs in the set of integers, right? So the Fourier transform of capital F is the same as the Fourier transform of small f. Therefore, this is nothing but the sum of f hat k e to the negative 2 pi I kx as k runs in the set of integers. And let us write the definition of capital F here. The definition of capital F is that f of x plus n n runs in the set of integers. Now what we are going to do? No. What are we supposed to prove? We are supposed to prove that the sum of f of n is the same as sum of f hat of n, as n runs in the set of integers. We are almost done. So from this step, what do we need to do? Like, this is true for all x, right? So we need to pick a particular value of x.
0.
Exactly. So plugging in x equals to 0 gives us, on the left hand side, we have sum of f of n, as n runs in the set of integers. On the right hand side, we get, so this exponential term becomes 1. So we get sum of f hat of k as k runs in the set of integers. And we're done. Okay. Yeah. Now we are going to derive the Fourier coefficients of the Eisenstein series, but I think now is a good time to take a 5-minute coefficients of Eisenstein series. Buckle up because we have a lot of complex analysis to do today. So let us recall the definition of Eisenstein series again. So GK Z is defined as a summation of 1 over mz plus n to the power k. Okay, and yeah, and we can separate the sum as follows. So we can write it as, so we can separate the part where m is 0 first. So sum of n being negative infinity to infinity, sum of 1 over n to the k. So this is the part where m is 0, right? And yeah, sum where m is positive, n being negative infinity to infinity, sum of 1 over mz plus n to the k, and the part where m is negative. So n is negative infinity. Okay. So this. And now notice the first term. Does the first term look familiar to anyone? This is the twice of the zeta function, right? Because the zeta function contains only the positive ones. So this is the twice of the zeta function. And this is twice because k is an even number, right? If k was odd, then this sum would vanish, right? Okay. And also, do we see any similarities between these two terms where m is positive and m is negative? I have a clue for everyone. That is, we have proved that the Eisenstein series converges absolutely and uniformly, because the uniform convergence guarantees us that this is a holomorphic function. Okay, so what is the relation between these two terms? The terms where m is positive and the terms where m is negative. Yeah, they're exactly equal. So why is that? Because if, let's say, if we take m equals to -1 and n equals to some other value here, okay, so this is in the second sum, right? So this term is exactly the same as 1z minus n to the k, because k is an even number. So all the terms in the second sum are in the first sum as well, and vice versa. So therefore, these two sums are the same. So we can combine them to write plus 2 times sum of m greater than 1, n being negative infinity to infinity, 1 over mz plus n to the power k. Okay. So, yeah. And the inner summation right here, this looks like a sum of 1 over w plus n to the k. So this is of the form like this, the inner sum. Right? So, and this is periodic with period 1. Is that clear to everyone? Well, here I've taken w to be mz. So this is periodic with period 1 because this sum is absolutely convergent. So we can rearrange the terms. And so since this is periodic with period 1, so our key idea is to write this uh, as a sum of something times e to the 2 pi I n omega. N is integer. No, sorry. N is not integers. N is just. So our idea is to show it as a sum like this, because since since this is uh, periodic in W with period 1, so if we change W to be, if we change W to W plus 1, then also this stays the same. So our idea to show it as a sum like this. So now let us try to prove this. For this, we are going to use, wait. No, I think it's n is integers. Sorry. Yeah. Yeah. I think this is the correct one, because we are going to use Poisson summation formula for this. Yeah. So we are going to use Poisson summation formula to show that these two are the same, and for that, both the summations are indexed with the set of integers. Okay, but in order to apply the Poisson summation formula, we need to verify a couple things. What are they? That is the function f that we will be Fourier transforming, that is this one for our case. Let us write that phi sub w of x is 1 over w plus x to the k, right? And we are going to take the sum of phi w of n, and we're going to show that this is equal to the sum of phi hat w of n. But for that, we need a couple things. That is, phi w is continuous and absolutely integrable. Also, phi w hat is continuous and absolutely integrable. Because if we look at the proof of the Poisson summation formula carefully, then we can see that we have used the fact that we can we can rearrange the terms of the sum, and that is guaranteed by absolute convergence of both the function and its Fourier transform. Okay. So we need to verify these things. Well, first things first, the first one, phi w is continuous, so it's obvious, right? Because it's a yeah. So we are considering this as a function from the set of real numbers, right? But this is not defined on negative w, but negative w is not on the real line. So this is continuous, clearly. Now we need to show that this is absolutely integrable. So let's try to show that phi w of x, the absolute value of that is 1 over, let's write w as a plus ib, and this is a plus x plus ib to the k, right? And this is nothing but 1 over a plus x square plus b square to the k over 2. So, and this is of the order 1 over x square, right? 1 over x square to the k over 2. And this integral converges. Like, converges for k greater than or equal to 2. Okay. So therefore, phi w is absolutely integrable as well. All right. Everything's fine. Now we need to find the Fourier transform of phi w. Fourier transform of phi w of x defined as 1 over w plus x to the k. Okay, so let's denote the Fourier transform to be phi w hat, and that at y is an integral e to the 2 pi I xy divided by w plus x to the k. And this is an integral over the whole real line. And we are now going to use the residue theorem to compute this integral. Yeah, it's dx. It's dx because y is a free variable right here. So, yeah, we are going to compute this integral using residue theorem. Okay. Let me write it a little bit. So this is equal to the limit as r goes to infinity of the integral negative r to positive r e to the 2 pi I xy w plus x to the k dx. Okay. Now consider this function, this complex function, that is e to the 2 pi I zy. So instead of the variable we are integrating over, so we are changing that variable by a complex variable z and this. So this function has a pole of order k. Where is the pole? That pole is z equals to negative w, right? Yeah. And what we are going to do is basically this. This is, let's say this is negative r, this is positive r. So at times we are going to take this contour for integrating. At other times we need to take actually the other one, the contour downwards. Like why we shall soon see. Okay, first of all, the pole of order k, that is in negative w. We know that w is in the upper half plane, right? Because we define w as mz, where z is in the upper half plane. And we took m greater than 1. Do you remember? Like we rearranged the sum and we took the only the m greater than 1 part. So m is positive, z is in the upper half plane, therefore w is also in the upper half plane. So the pole is somewhere here. Okay. Yeah. Also, the absolute value of hz is equal to the absolute value of e to the 2 pi I zy divided by the absolute value of w plus z to the power k. Right? And this is equal to e to the negative 2 pi imaginary part of z y divided by, right? Okay, uh, and we need to take a contour in such a way that the semicircular part, so the value of h on that semicircular part vanishes as r goes to infinity. Like we need to choose a contour in such a way. Well, that's how we do contour integrals, right? Because otherwise, the contribution from the semicircular curve is also present in our integral, which we don't want. Well, we want only the contribution of the real line, right? So therefore we need, like, what do we need? We need that as r goes to infinity, the absolute value of h on the semicircular path, approaches 0. Okay, so yeah, so this is what we need for doing the contour integral. Now, so yeah. So remember, we are integrating over z. And what is y? Y is our free variable right here. Okay. Now, so depending on the value of y, we need to choose one of these two contours. Okay. So if y is positive, then can someone tell me which contour should we take? If y is positive, like for which of the contours, like this expression this is not a rectangle, so this expression vanishes as r goes to infinity. Yeah, for y positive. Yeah, exactly. Right. So for for positive y, e to the negative 2 pi imaginary part of z times y. So we need this to go to 0 as fast as possible, right? Yeah. So we need these to go to 0. So therefore we need to choose the upper half contour. So what is the upper half contour? That is, this is negative r, this is positive r, this. And h has no singularities in the inside of this curve. Therefore, let's name the contour CR. Therefore, h of z dz CR is 0. So clearly, like, as we take the limit as r goes to infinity, let's call the semicircular path SR. Okay. So this is the path from negative r to r, and SR is this semicircular path of radius r centered at 0. So yeah, this goes to 0 as well, because, well, of course, the term in the square bracket is always 0. So as we take the limit will also be 0. And limit is distributive, so we get that integral of negative infinity to infinity h of x dx it doesn't matter if we change the integration variable, of course. So, and limit r goes to infinity, integral sr h of z dz is equal to 0. And we have like chosen the we've chosen the upper half curve because on the upper half semicircular path, the absolute value of h goes to 0. And it goes to 0, like, it decays exponentially because it's e to the negative 2 pi, imaginary part of z, y is positive, imaginary part of z is positive. So it decays exponentially. That is why we can say that this limit is 0. So, therefore, for y positive, this is equal to integral of h of x dx, negative infinity to infinity, this is it. If y is positive. And we are yet to do the part with y being negative. So let us do it real quick. If y is negative, then we are going to choose the lower half contour. But this time we have a pole. Let's say right here, this is negative w. Oh, I just realized I'm probably like saying w and omega interchangeably, which I probably shouldn't have. But yeah, they look identical. So yeah.
By positive, you mean non-negative.
Yeah, by positive I meant non-negative. Okay, so if y is negative, then let us choose this contour. And again, yeah. So what is the integral of h of z dz over cr? So let us remind all of us that h of z is equal to e to the power 2 pi I zy, right? 2 pi I zy divided by w plus z to the power k. No, we have a pole here, so it should be the residue of f at the pole, right? Yeah. And this path is oriented clockwise. So we have a factor of negative 2 pi I. So if it were oriented counterclockwise, we would have a factor of positive 2 pi I. 2 pi I, the residue of h at z equals to minus 2. Okay. And of course, the right hand side is a constant. So the limit as r goes to infinity, again, let's call the semicircular curve SR. This is negative r to r h of z dz plus SR h of z dz. This is equal to negative 2 pi I, the residue. All right. And again, we are going to like distribute the limit, and this term right here, this term will vanish. So therefore, the integral negative infinity to infinity h of x dx is exactly the same as negative 2 pi I, the residue of h at negative w. Now we need to find the residue. So here the point of singularity is a pole of order k. Do we know the formula for evaluating the residue for such poles of higher order? Yeah, I have it written down right here. Yeah, you have to differentiate it k minus 1 times. So residue of h at negative w, this is the same as 1 over k minus 1 factorial. Then you need to take the derivative k minus 1 times of what? Of like z plus w to the k h of z. And you need to evaluate this derivative at the point we are considering. So this evaluated at, how do I like shift it to the left? No, this is not. Yeah, perfect. I'm slowly learning how to use an iPad. Yeah. So this is the formula for evaluating the residue in a point of in a pole of order k. Okay, and it's very easy to verify now. So this is 1 over k minus 1 factorial. This is like the kth derivative. So let me write it. D is at k minus 1 of something evaluated at negative w. So what is this something? So h of z is what? H of z was e to the 2 pi I zy divided by w plus z to the k, right? Yeah. Now we need to just take this derivative k minus 1 times. So let's take this factor right here. And if we take the derivative k minus 1 times, we have a factor of 2 pi iy k minus 1 times. Is that right? And then we have e to the 2 pi I zy. But we are evaluating it at w, so that's why this z will be replaced by negative w. Okay, so this is the residue. Therefore, the integral of h of x dx negative infinity to infinity is equal to we have a negative sign in front, right? So negative, I have 2 pi I to the k minus 1 and 2 pi I right here. So 2 pi I to the k divided by k minus 1 factorial. And then y to the k minus 1 e to the negative 2 pi I w. And this is of course if y is negative. So therefore we have found that the Fourier transform of phi sub w at y is equal to, this is defined piecewise. So that's 0 if y is non-negative, and it's equal to this formula right here. How do I copy this? Yeah, perfect. Yeah. Okay. We need to verify now a couple things. That is, this function is continuous and absolutely integral. Then we can apply the Poisson summation formula. So how can I see that this function is continuous? We just need to check at y equals to 0, right? Because both the pieces are continuous. So we need to check in the, yeah, so we need to check in the point y equals to 0. So if y is 0, then what do the second part tell us? The second part has a term y to the k minus 1. So that second part is also 0. So it's obviously continuous. But is it absolutely integrable? Well, let's see. What is its absolute integral? That is, and well, this is a constant term, so we are going to ignore it for now. Okay, so let's call this constant box, and this is an integral. Sorry, I have an integral right here. Also, integral dy. Y to the k minus 1, e to the negative 2, the absolute value of this thing, right? So what is the absolute value of this thing? That is e to the, well, let me write it here. The absolute value of e to the negative 2 pi I wy. What is this? This is e to the 2 pi imaginary part of w times 1. Okay. So this is, we don't have a negative sign here. Yeah, that's what I was missing. Yeah. Now, this integral looks very familiar, right? Yeah, because if y is positive, then this function is 0. This one, no, because what is w? W is just like real of w plus I imaginary of w. So this I and this negative I multiplied and gives us 1. Okay. Okay, I think I can write this integral in a slightly more familiar way. That is, I can change the variable to y to negative y. So then the integration becomes from 0 to infinity, y to the k minus 1, e to the negative 2 pi imaginary part of w, y dy. Now, does it look familiar? Fourier series. No, there's no I in here. Exactly. So gamma function, so this is gamma, right? Yeah. So gamma of k is this integral. U to the k minus 1, e to the minus u, du evolved from 0 to infinity. So we just need to change the variables a little bit, then we'll have a constant factor in front. And this is obviously bounded. And this is bounded by gamma of k. And what is gamma of k? Gamma of k is k minus 1 factorial times some other constant factor. Well, we don't really care about constant factors. We just care about the fact that they are constant. So therefore, phi w hat is absolutely integrable. Now, let us bring out the big gun, the Poisson summation formula. So I think it's better if I write our functions once again. Okay, and the Fourier transformation of y, sorry, Fourier transformation of phi is this. Wait, what? Copy. Okay. So if we now apply the Poisson summation formula, what does that tell us? That tells us that the sum of these as x varies in the set of integers is equal to the sum of this as y varies in the set of integers. But we only need to we only need to consider the negative integers for the second term because phi hat is 0 if y is non-negative. So therefore, the sum of 1 over w plus n to the k as n runs from negative infinity to infinity is equal to a sum. This is a constant factor, so let's copy it. And then we have a sum. The sum of n to the k minus 1 e to the negative 2 pi I factor n. Right. Now if we change n, then we get, if we change n to negative n, then we get that this is again another sum. I think I've copied the image, right? Yeah. Nice. Negative n to the k minus 1. K minus 1 is odd. We need to remember this, of course. 2 pi I w. So k minus 1 is odd. There comes a negative sign from here, and we have negative sign here. So those two negatives cancel each other. So we have again best get rid of the negative sign and get rid of the underlines again. Sum of n to the k minus 1 e to the 2 pi I. Okay. So yeah, we are almost done. Let us get back to our favorite Eisenstein series once again. GKZ. There was 2 zeta of k plus 2 sum of m greater than 1 sum of mz plus n to the k. Right. We replaced mz by w. Get it. My zeta doesn't really look good. Yeah, zeta and phi almost look identical. Okay, plus 2 sum of m greater than 1 and yeah, this is a really long one, so yeah, 2 pi I to the power k minus 1 factorial, and then we have a sum. This sum is over n equals to 1 to infinity. N greater than 1, n to the k minus 1, e to the 2 pi I, and omega is mz. Right. Okay. Now what? Now this is the Q of Z, right? So everything is as before, 2 zeta of k plus 2 sum 2 pi I to the, I think I can bring the 2 pi I to the k in front because that's just a constant. K minus 1 factorial. We have a double sum. M is greater than 1, n is greater than 1, n to the k minus 1 times q to the mn.
This is the Q expansion.
Well, not quite, because in the Q series expansion we only have a single sum. We don't have a double sum. So we need to like tweak this sum a little bit. So for that we'll do a change of variables. That is, we'll take mn to be n, and we'll take n to be a divisor of capital N. And guess what? 2 zeta k plus 2 pi I to the k minus 1 factorial. Sum over n, sum over all the divisors of n. The divisor to the power k minus 1, q to the n. And n is, of course, 1 to infinity. So, yeah, now it's the Q series expansion. And this sum right here, sum of n divisor of n, n to the k minus 1. Is anyone familiar with this sum?
This is another
Yeah.
divisor function.
Yeah, thus when k is equal to 2, that is like basically the sum of d as d divides n. So this is called the sum of divisors of n. As we increase the power of n, this is called sigma sub n. So sum of the nth power of the divisors. So therefore we have our
This is another arithmetic.
yeah. So this function is very interesting in number theory. So, and of course it's of no surprise that a lot of the properties of this function arises from modular forms, because we're saying it right here that the Q series expansion of our favorite modular form, the Eisenstein series.
Function has gamma function,
Well, it doesn't have gamma function yet.
k minus 1 factorial.
Yeah, we have well, yeah, it has gamma function as well. It it has zeta function, and it has the sum of the k minus 1th power of divisors. So yeah. Let me try to write it from my memory to see. So plus 2 pi I to the k minus 1 factorial, sum of n sigma k minus 1 of n. Yeah, I think it's correct. So yeah, there we have it. The Q expansion of the unnormalized the Q expansion of unnormalized Eisenstein series. Okay, but what does this normalization mean? So what was the formula for EK, the normalized Eisenstein series? That was, yeah, summation of
1 by m square
M and N are coprime.
that is
Yeah. And this is equal to what? 1 over 2 zeta of k gk. Well, this was a homework, right? And this is really easy to show, because if we take this series where we are taking all the sums, so we can group the terms, like, yeah, yeah, exactly, yeah. So let's say we can group the terms with GCD1. We can group the terms with GCD2. Then we can group the terms with GCD3, and so on and so forth. Right. So, and if we like take all the terms with GCD2, then we can like take a 2 to the power k term in front, right? Then we have the Eisenstein series, normalized Eisenstein series. So yeah. So therefore, the Q expansion of the normalized adjacency series is 1 plus 2 pi I to the k minus 1 factorial zeta of k, and this sum. So by the term normalized, we mean that the first coefficient is 1. And the first coefficient is really significant because what does the first coefficient indicate? It indicates the limit of the modular form as the imaginary part goes to infinity. So yeah, if that is 1, then we call the isomorphism series normalized. Otherwise, that's the plain unnormalized isomorphism series. Yeah. I have just one more thing, that is about Bernoulli numbers. So the Bernoulli numbers are defined like this. It's the x to the e to the x minus 1. So we can take the power series of this function around 0. So that power series of the form like this. That something times x to the k. Right? So this is the form of the power series. So if we take this term and divide it by k factor, so these bk's are called the Bernoulli numbers. And Bernoulli numbers are like really significant in combinatorics and graph theory as well. Well, graph theory is a part of combinatorics. And there's a really cool formula of the zeta function involving the Bernoulli numbers that Euler proved. So Euler's formula. Yeah, maybe Euler should have derived a formula to compute which formula of his is that formula. Right? There are so many Euler's formulas. Okay, the Euler's formula is that zeta of k is equal to negative 2 pi I to the k minus 1 factorial dk by 2k. So this is Euler's formula, and using this formula we can write the Eisenstein series, normalized Eisenstein series like this. Ekz is equal to 1 minus 2k by bk and this sum. Okay, I want to end with a very interesting comment. So I think I've mentioned it before that the modular forms of weight k forms a vector space, right? We can add two modular forms of weight k and get another modular form of weight k, and we can multiply it by a scalar. By scalar, I mean a complex number. And well, of course, and today we have seen that to each modular form there is there's power series attached to it, right? And we can take the vector space of all the power series as well, right? All the power series, they form a vector space as well. But that vector space is infinite dimensional. However, the vector space of modular forms is finite dimensional. So the vector space of modular forms is a finite dimensional subspace of the infinite dimensional space of power series, or you can say that the infinite dimensional vector space of holomorphic functions on the upper half plane, right? So this finite dimensionality, so well, I think I can write something that, let's say f of z, f is a modular form, and we can write a n q to the n. It's the q series expansion, right? We have like infinitely many coefficients, but we don't have infinitely many independent choices because the vector space is finite dimensional. So the coefficients are not independent. Okay, is that clear? So if the coefficients were all independent, then we would have infinite infinite degrees of freedom. But our vector space is finite dimensional, so we don't have infinite degrees of freedom. We only have finite degrees of freedom. So although we have like infinitely many parameters, we only have finitely many degrees of freedom. From that, there arises some really like
Constraints.
yeah. So from that we can achieve like some conditions between these between yeah. So from that we can derive some interesting conditions between these Fourier coefficients, and we have seen that the Fourier coefficients are some really interesting number theoretic functions. So we can actually derive some like very interesting number theoretic formulas from just the construction of modular forms. So these are some of the things we'll be seeing in near future. So if anyone have any question, please feel free to ask. Otherwise, let's end this here. Okay. Okay. Then let's end the recording.